Good morning. Welcome to this course on Advanced Computer Algebra. This course is part of our master's curriculum in computational mathematics at Johannes Kepler University in Linz in Austria. And it's called Advanced Computer Algebra because it's designed as a continuation to the course Computer Algebra, which is part of our bachelor's curriculum. So the assumption is you have attended the course on Computer Algebra and want to know more about the subject. What is computer algebra? Computer algebra is about computation without approximation, in particular computation with polynomials. And I will assume that you are somewhat familiar with computation with polynomials, especially polynomial arithmetic and the Euclidean algorithm and its main applications. So this would be covered in the bachelor's course in computer algebra. And then there are several possibilities how we can continue for a course in advanced computer algebra. Computer algebra is quite a diverse area. We could go into the direction of Gröbner basis and nonlinear polynomial systems. We could go into algorithms for differential equations or symbolic integration, or we could go in the direction of symbolic numerics, combination of numerical computing with symbolic computation. Or we could do fast linear algebra, exact linear algebra, or algebraic number theory. That would also be a topic. And here in Linz, you are in the fortunate situation that there are specialized courses for many of these subjects. So for the advanced computer algebra course here, I will just continue on the fundamental algorithms, talk more about the fundamental algorithms on which all these other things that I mentioned are based, so that it's a natural continuation of the Computer Algebra 1 course. So we will continue to talk mainly about polynomial arithmetic. That's the plan. So there's a book, standard reference in computer algebra, modern computer algebra book by von Surgaten and Gerhard. And it has several parts, and I will cover some of these parts. So there's a part 1. Part 1 in the book is essentially what I will assume that you have done in computer algebra 1, and then we will cover part 2 and part 3. Part 2 is about fast algorithms, fast polynomial arithmetics, and things that you can compute fast. How fast can you do things in polynomial arithmetic? And part 3 is about polynomial factorization. So this is roughly the plan for this course. Why is this course on video? My experience with the course in the past few years is that there's very little interaction between me and the students in class. I want to have more interaction with you, and that's the reason why I do videos. So that seems contradictory maybe at first, but the idea is I'll do the explanation, the presentation of the material in the videos, and then from time to time we have a personal meeting which is exclusively dedicated to discussions, and I hope that this will lead to more interaction between you and me, and where we can discuss the matters that you have seen in the videos better than we would discuss them during class when you see them the first time and have no chance to come up with a question. Okay, so details about this and the meetings, place and time will be announced on Moodle. So I mentioned already that there are three, that we cover two parts of this book, Modern Computer Algebra. Let me show it again. This one, we have it in the library also. I will not follow the book step by step. I will use my own notations, and I have sometimes the things that I skip, because there's a lot of material in the book and we cannot cover everything. There's also sometimes something that I do that is not in the book. I will mention this if this happens. And of course everybody has his own notation and his own preferences on how to present. But you will have you won't have any difficulties I hope, to connect what I'm talking about to what is written in the book. And there are lots of further details in the book. So I said already, the first part of the course is about polynomial arithmetic. So let's maybe fix a little bit of notation before we get into the subject. So I will use K, or maybe K, capital K or small k, it's hard to distinguish in my handwriting, for field. So this should be a field. Maybe sometimes I use this symbol, it should also be a field. And the field, I don't think about real numbers or complex numbers. Think about fields in which we can compute. Maybe the rational numbers or a finite field. So we don't want to compute with approximate numbers. We want to compute with in fields where every element has an exact representation. Okay. Then if I need a ring, then I will typically use it R. Call it R, and ring this will be always commutative. I think we won't have any non-commutative rings in this course, and it will have a 1. And I said already we don't want to compute with approximate numbers, but I should say explicitly we want to compute. So there are fields in which you cannot compute and rings, and the assumption is always that when I write let K be a field or let R be a ring, that these are rings in which you can compute. So this means that there are some ways to perform addition and multiplication and to check whether a given element is the zero element, which is the same as being able to decide whether two given elements are equal, because every element has some way how it can be written down, but that way may not be unique. So there is a question of whether two expressions that represent an element of the domain under consideration are equal or not, and I assume that this can always be decided. So if P is a vector, or a polynomial, then its coefficients, or its, if it's a vector, its coordinates, coefficients are denoted P0, P1 up to however long it is. And so that means P is P0 plus P1x plus P2x squared plus and so on, if it's a polynomial, or P equal to P0, P1 up to Pn minus 1 if it's an element of, let's say, k to the n. It will be convenient to assume that a polynomial or a vector also has coefficients or coordinates outside its range. I will just make it 0. So convention Pi is equal to 0 if I is less than 0 or I is greater than the degree of P, which I will write like this, degree of P if it's a polynomial, or greater than n if it's a vector. The degree of 0 is minus infinity, in case this is perhaps in doubt. And yeah, and when I write log n, then I usually mean the log to base 2. And we will use, we will talk about complexity, we will talk about how much things cost. So we will express this in terms of the O notation that you surely have seen in other courses already. So we will write f of n equal to O of g of n, with the meaning that there exists a c positive and n0 also positive, such that from n0 on, the f is bounded in absolute value by the g. This is probably familiar. And there's another notation which I'm not sure how often I will use it, but it's frequently used in the book, and it's very convenient. You know that the O notation was invented to focus on asymptotic behavior of the function. We want to know not exactly how many operations are needed, but we want to know how does this grow if n is very large. That's one aspect of the O notation, and the other is the one that I omitted here. The other one, the other aspect of the O notation is that it focuses so much on the growth type of the function that it even suppresses multiplicative constants. So the condition here is not that the absolute value of f is less than g, it's actually less than c times g for some c that exists. And sometimes, so why do we suppress constants? It is of interest whether one algorithm is twice as fast as the other. So that would be a constant of 2. It's not something that we don't care about. It's just a bit our laziness that in a complexity analysis, figuring out the constants is often more difficult than figuring out the big O. So if we get the big O, and we are already happy because we somehow know in which direction does it go. And sometimes we are even more lazy and want to suppress not only the multiplicative constants but also the logarithmic parts. So we introduce another notation for this. Let's say f of n is O tilde of g of n if there exists a k positive such that f of n is equal to O of g of n times log g of n raised to some power. So the log goes to infinity, but it goes very slowly, and powers of it go more quickly, but still very slowly. So this one grows, but it grows much less than this one. So it may be fair, it grows exponentially less, this one than this one. So it may be fair to say this growth is essentially the growth of g, not up to a constant factor, but up to logarithms. So that's still, it's dominated by g. G tells me how it goes, and then it goes a bit more than that to infinity. Okay, so much about notation, and now let's do something more serious. And I told you I will mention if I do something that is not in the book. I will start with something that is not in the book. We will talk about fast multiplication for the next few units in this course, and I want to start with something that I like to call semifast multiplication. Semifast. And what do I mean by semi-fast? I mean it's fast in theory, but not fast in practice. And that's not what we are interested in most of the time. I will just show you this as an example for how complexity analysis can look like if you're a theoretical computer scientist, or if you care about algebraic complexity. If you really just care about how does it go asymptotically, you don't care how does it work for big things in practice, then the reasoning can look like what I'm going to show you today. But this is really an exception. It's not what this course is about. We are really caring about things that are fast in practice for actual computations. And we use the theory later to develop algorithms that are fast in practice. And then typically they will be fast both in theory and in practice. It's not always a complete agreement, a complete match, but but it's not sufficient for us to just prove some bounds that have no relevance in practice, except today. So what we will do is, let's say we have a ring, and we assume that R is, we say R is a ring, and it's infinite in this section. And the task is given f and g in Rx. Let's say the degree of f and the degree of g is less than n. Find h, the polynomial h, which is defined as the product of f and g. Now, if I say given is a polynomial, then I always mean given is a list of its coefficients. And if I say find a polynomial, then what I want to have is a list of its coefficients. So more precisely than written here, I should say given the coefficients of a polynomial f and the coefficients of a polynomial g, both of which have a degree less than certain n, we want to compute the coefficients of their product, called h. Now that's an easy thing to do, because you can do it just by how the multiplication is defined. That's the most straightforward algorithm. It says that the kth coefficient of the product can be obtained by a sum I from 0 to n minus 1, to n, whatever, to n or to n minus 1, fi g k minus I. Now here I'm using the convention that if I'm out of range, that this will be 0. So you do this for every k, from 0 to n, or to 2n minus 1, and that's it. And you have the coefficients. It's obviously correct because that's how they are defined, but that's a bad algorithm, because this sum is a sum of length n, and we have to do n products of elements of R, and then as many additions. So the computation of one of these h's takes linear time, but I have a linear number of them, so altogether I have quadratic time. So this takes of n square operations in R. And there are many parts in computer algebra where you would be very happy to have quadratic complexity, n square. Often if you think of Gröbner basis or more complicated operations, quantify elimination, and things can be exponential or double exponential or whatever. So quadratic complexity is not so bad. But in this course we are not happy with quadratic complexity. We want to have this faster. And well, there's a way of doing this faster. You may have seen this. This is Karatsuba's idea. Karatsuba observed that if you have two polynomials of degree 1, you multiply them out and collect terms, and you get this expression, where it seems at first glance that you have to do 4 products. You have to compute each of these 2 coefficients with each of these 2 coefficients. That's 2 times 2, and 2 times 2 is 4. So we have 1, 2, 3, 4 products to carry out in order to get this product, unless we realize that we don't need this product and this product. It's sufficient to have their sum, and to have their sum, which is this one, we can get along with 1 product less, 1 multiplication less, by taking the product of the sums. If I take the product of these sums, this one like this and this one, if I compute this product and multiply it out in my mind, not in the computer, just if I think about what this is, it's the sum of these 4 terms. So if I subtract this one, and then this one and this one disappears, and what remains is exactly what I want. So altogether I have just three things that I need to compute. I compute this one, the yellow one, the blue one, and this white one. That's three multiplications, and then from the white one and the yellow one and the blue one I get the green one. I've saved one multiplication in the task of computing the product of two polynomials of degree 1. So that doesn't help very much, because we care about big polynomials and not about polynomials of degree 1. But the idea is to do this recursively. So you take a big polynomial and you split it into pieces. So you have the f maybe it looks like this. Sorry. And the g as well. And it may be a polynomial of very large degree, but you split it in the middle and consider it as a polynomial with polynomial coefficients. So maybe this goes from x to the 0 to x to the n, and then somewhere here you have x to the n half. So you write this as a polynomial, you write f as something plus something times x to the n half. And this are polynomials of degree x to the n half. And then you use the observation of Karatsuba to multiply these polynomials of half the degree. So in G you write it as well like this. So you have reduced one product of two polynomials of degree n to three products of degrees of half the size. If you write this down, you get this algorithm. So here f and g are the given input and h is the output. And so this is a recursive algorithm, and in a recursive algorithm you always have to say when does it stop. So it reduces the problem to a problem of similar nature, of the same nature, but of a smaller size. It keeps doing this, but at some point it will have a very, very small problem. For example, a problem of multiplying degrees of degree 0. If you are at this situation and here n is 1, then you just compute the product somehow. It's just a single ring operation. And otherwise, you do the splitting that I indicated. So on the slides and in the notes, I often use upper index, like here, f up 0, but then with parentheses around it so that we don't confuse it with an exponent. Because I want to avoid that this clashes with the convention that the coefficients are denoted by the subscripts. So f0 is a polynomial with index 0, and it has coefficients f0, 1, 2, 3, 4, 5 with subscripts. Okay, and f1 and g. So they all have half the degree of f and g. And then I compute u 1, 2, 3 as on the previous slide, and I return this result. This is Karatsuba's algorithm. So this is faster than quadratic time. It needs only n to the 1.5, and it's a useful algorithm. It's not the algorithm that I said at the beginning we will do something useless today. This is not yet useless. It's not the best that we have, but it's also not the worst. It's better than the quadratic algorithm, not only in theory, but also in practice. So where does this theorem come from? It comes from a complexity estimate. You say what is the runtime? What is the number of operations that this algorithm needs if I apply it to input of size n? That's what the theorem makes a statement about. That's what we want to know. That's what we want to estimate. And the recursive structure of the algorithm translates into a recursion for the runtime. So we can say, in order to multiply two polynomials of degree n, I have to do I have to spend, I can get along with 3 multiplications of half the size, which I work out with the same procedure. So they take time, take a number of operations, that is t of n half, plus, well, and then I need a little bit of time to do the rest of the work. But what is the rest of the work? So the rest of the work is the additions here. So here I have polynomials of degree n, or n half. I think here they are degree n, because they are obtained as products of 2 polynomials of degree n half. So here I have polynomials of degree n, and I have to add and subtract them. But that's cheap. If I have to add 2 polynomials, I have to just add all the coefficients together, but there are n coefficients, so I have to do n additions. That's it. There's nothing else that I have to do. And otherwise, I'm not doing anything. Oh, here's an additional addition, but addition is cheap, as we just said. Here's one, and this here is nothing. What happens here in step 2 is just split the polynomial in the middle. That doesn't cost anything, because when we talk about multiplication or complexity, we count the number of operations in the ground ring. And splitting a polynomial in the middle doesn't require any addition or multiplication or any comparison even in the ground ring. So this is for free. So this means here I have that Tn is bounded by 3 Tn over 2 plus, well, something that is linear. And there's a general theorem that says how you can solve these recurrences. I'm not going to do this here. You can do it as an exercise if you like. From here you can prove by induction that T of n is what the theorem says. N to the log 2 to the log 3 to the base 2. So the 3 comes from here and the 2 comes from here. And so the general theorem that tells you what the solution of these recurrences is goes with, well, it has a p here and a q here, and then some exponent here, and then it has a case distinction on whether this is larger than this, or whether this log of this one to the base of this one is larger or smaller or equal to this exponent here. And depending on this, it's either the log that wins, or it's this exponent here that wins, or if they are equal, then you get an additional logarithmic factor. Okay? But let's just believe this for the moment, and return to the discussion of Karatsuba's algorithm. Let's see if we can understand where this comes from. It's okay. It's formulas we can check that they work out, but where do they come from? So you can view this as an example of evaluation and interpolation. So what the Karatsuba does is it computes A, or it considers the first half, which is A, and the second half, which is B, and the sum of the 2 halves for each of the 2 polynomials. Now the first half is the evaluation of this polynomial at 0, and the sum of the 2 is the evaluation of this polynomial at 1. And yeah, well, the b, you can say this is somehow the value of the polynomial at infinity, if you wish. I wish. So let's say this. And if Karatsuba saves a multiplication, or manages to save a multiplication by this evaluation and interpolation idea, then maybe we can save more multiplications if we use more interpolation points. So let's see if this goes. That means we are going to design an algorithm that splits the 2 polynomials that we want to multiply into k pieces instead of 2 pieces. Okay? So in order to reconstruct a polynomial from interpolation points, you need as many interpolation points as the polynomial has a degree. Plus 1 or minus 1, never mind. So it's 2k minus 1 interpolation points. Okay. The evaluation of a polynomial at certain points, that I denote here by x1 up to x something, can be expressed by a multiplication with a matrix, by this Vandermonde matrix. If you think of multiplying this matrix on a vector, let's say the vector of the coefficients of f, then you will get the values of f, because you get f0 times 1 plus f1x plus f2x squared and so on, here for x1 and here for x2 and here for x3 and so on. So this expression here, v times the f vector, this is the vector of values of the polynomial f at x1, x2, x3 and so on. And here is the same with g. So multiplication by v is evaluation. And then this dot with the circle around is supposed to mean point-wise multiplication, component-wise multiplication, because you know that the product, the value of the product of the polynomials is the product of the values. So that's what this dot is supposed to do. This doesn't take a lot of time, because here I have n values, k values, or maybe 2k values, and I have to multiply them, so it just takes k time. And then I have to turn the values into the coefficients, but that's the same as what the v does, just in the other direction. So what I have to do is compute the inverse of v and multiply it on this value vector of h, and then I get the coefficients of h. Okay? So I have here the interpolation, here an evaluation, there an evaluation, and here the component-wise product. And I fix a k, like Karatsuba fixed k equals 2, and then he had 2k minus 1 being 3. Now I fix maybe another k, and for a fixed k I pre-compute this matrix and its inverse, so that I don't have to worry about what the cost of computing this matrix is. I compute it just once, and once and for all, and then I put it into the code. And the inverse I'm also not going to compute. So then I can formulate this algorithm, this generalization of Karatsuba's algorithm, exactly the same idea as Karatsuba, and exactly the same input and output. And it's actually not one algorithm, it's a family of algorithms. For every k you get such an algorithm. So what does it do? If the degree n is less than a certain fixed bound, then you just compute the product somehow. Whatever you do is fine. Otherwise, if the n is larger, then you split the two input polynomials into k pieces, like here, as indicated here. And the k pieces all have degree k, n over k. And then you do what I just described. You apply v to these pieces, the vector that contains these pieces. Now these are polynomials, but the entries of v are just ground field elements. Okay, but then you multiply these resulting vectors. So that would be a multiplication of polynomials again, and these you do recursively. You call again this algorithm, and you call it with several inputs of not half the size, but 1/4 of the original size. That's happening here. And then you get a bunch of vectors as return, in return, or as return values, as results. And then you apply the inverse of v to it, and the inverse we don't compute. We have computed at compile time, if you want, or at programming time. We apply this matrix to h. That's the computation we have to do, and then we return the result. So what does this cost? Now here's an illustration that shows that f is a very big polynomial. It's split into pieces, but the pieces are still polynomials. So these polynomials are here in the vector, so they are indicated by these lines, and I have to fill them up with 0 because I have to get as many values for the evaluation interpolation as the product is long, and the product is about twice as long as the factors. So that's why there are the zeros. And these green dots indicate that the elements of V are not polynomials but ground field elements. So what is now the cost here? The cost of multiplying this matrix with this vector depends on the size of this matrix, but also on the length of these polynomials. So the length of these polynomials is n over k, and the matrix is essentially k square. So I'm doing k square times n over k many operations if I multiply this matrix to this vector to obtain this one. So what do we gain by this? What is the efficiency of this algorithm? Well, and more precisely, how does this efficiency depend on k? We have seen already the efficiency for k equals 2, which is just exactly Karatsuba's algorithm. But how is it for other k, or how is it in general? And the theorem says that you can make you can get arbitrarily close to linear time. So for every fixed epsilon, there is a multiplication algorithm for polynomial that multiplies polynomials in Rx and needs just an exponent of n that is as little more than 1 as you desire. So I guess I have to prove here. The proof is very simple. Usually I will do the proof handwritten so that I slow down, but this proof is very simple, so I will put it on the slides. It's the same recursion as before. So for fixed k, the runtime is estimated by this, so it's Tn is equal to, that's the number of recursions, this is okay, so for fixed k, this is the complexity. The algorithm breaks the problem of size n into so many problems of size k, n over k. This is what happens in this step. This is the recursive call, where h is a vector of size 2k minus 1. Okay, and this is what we discussed as the complexity of this matrix vector product, which is also, of course, the complexity of computing the inverse of v to it, to a vector. So it's k squared, the size of the matrix, times n over k, the length of the entries in the vector. Well, altogether, this is, well, k is a constant, so we don't care, it's linear in n. And you use the magic theorem to say that this complexity is O of n to the log k, the k from here, times, log of this one from here to the basis of k. Okay. Now, which k is the best? Well, there is no best k. It gets better and better as much as you increase the k. The greater you make the k, the smaller this logarithm becomes. You see this by using L'Hopital's rule. If you take this limit of this logarithm is the quotient of this logarithm. If you send k to infinity, then both parts of the fraction go to infinity, so you can differentiate here and there, and then you see the quotient of these two fractions goes to 1. So this goes to 1. And it goes to 1 from above. And that's exactly what the theorem says. The theorem says you can get as close as you wish to 1. But still, with this algorithm, you're still a little bit above 1 for every choice of k. You can go a step further and say, I want an exponent that, well, is better than each of these exponents. So this is the next theorem that says there is a multiplication algorithm for polynomials over a ring R that needs this complexity. Now, where does this come from? Now, here the idea is that you use the algorithm from before, this generalization of Karatsuba's algorithm to arbitrary k, but you don't choose the k upfront fixed, but you choose it according to the size of the input. So you choose the k adaptively in the algorithm, and you adapt the choice of k to the size of your input. If your input is very big, you choose a large k. If it's not so big, you choose a smaller k. So how do you do this precisely? Let's see. So here's a proof of the theorem. So the idea is adapt the algorithm to such as to choose a certain k independence of fn, and which k would you suggest? Now that's not an obvious choice. Here's the choice that works. You take k as 2 to the 2 squared log n, and then this means round below, round to the next smaller integer. So you use this dynamically. Dynamically, by this I mean that you're not choosing this at the beginning of the algorithm and then keep using this k, but in the recursion, and at every level of the recursion you make a new choice. So the algorithm reduces a certain problem size to a smaller problem size, so that means you're calling the algorithm again with a new n, and for this n you choose its own k. So you can choose different k's at different recursion levels. That's what you will do. Okay, so now let Tn be the resulting runtime, or the runtime of the resulting algorithm. And now, okay, so I didn't show you the proof of this simple recurrence for Karatsuba, but now for this case, which is a bit more complicated, let's go through the details, and let's go through the induction proof that shows the claimed estimate. So we fix an n that is large. We can assume that it's larger than 16 without loss of generality, because I later need this, but that's okay because 16 is a fixed number, and almost every number is large compared to 16, and we are trying to prove an asymptotic estimate, so 16 is not going to hurt us. And suppose that the claimed estimate works for for every problem size up to a certain bound. Then we will show it also works for the next bigger problem size. So I suppose that T of m, so we will make a proof for n. So I should have said let n be an arbitrary problem size, and we will show something for T of n, and we make the assumption that T of m is something for every m that is smaller than n. And I will assume that it is what the theorem says that it is. I can write it in different ways. So there's a constant that is hidden in the O. Let's make it explicit. because otherwise there's a danger we will cheat in the proof. So let's call it C1, and then the exponent in the theorem was 1 plus 2 over log m, no, square root of log m. So now maybe that's not the most convenient way of writing it, so let's write it a little bit differently. Let's write m as 2 to the log m. Remember, log is always binary log unless otherwise stated. So this one would be 2 times log m plus 2, and now the square root cancels with the log. I get a square root left, but in the numerator. I can write it like this. So I'm supposing that this is true for all m that are smaller than n. And what is that? So now we have to see what happens with Tn. Yeah, what happens with Tn? Yeah, we have to go into the recursion that describes the structure of the algorithm. And the structure of the algorithm is that it will say, so this is bounded by 2k minus 1 t n over k plus O of, well, we had the k square n over k plus O of k square. Now this term here comes, that's the one that we had before. This comes from the multiplication, or from the evaluation and interpolation. That's the multiplication with v and with v inverse. There's this one. Now, this is a term that we didn't see before, because before k was constant, so O of constant is nothing, it's eaten by this one. This one is not eaten by this one, because this one here is just kn. Oh, actually it is eaten by it. Okay. But what I mean here is the term that refers to the computation of v and v inverse, because before we said the v and the v inverse that are just computed once and for all at the beginning, at the programming time. But now I'm choosing a k depending on the input size, so I can't prepare all the necessary v in advance. I will have to compute them as needed. But that means I have to solve an interpolation problem and an evaluation problem, and you know from computer algebra 1 that this takes quadratic time. So this is what this term here is accounting for. So this is a computation of v and v inverse. Okay. Okay, so let's see what this is. So this is now this gets a little bit complicated, but let's see if you can get through this. Maybe the minus one doesn't matter so much. So let's say this is 2 times k. Now I say what is our k. Our k is this. So it's 2 to the what was it? 2 square root log n times now n over k is smaller than n, so I can use the induction hypothesis and take this expression into here and get C1 2 to the log n over k plus 2 square root log n over k. And then I'm done with this term. Now the two other terms, well, they come with a big O, so the big O hides a constant factor. Let's make this constant factor explicit. I can take the same for both of them. Just take the larger of the two. So C2 times, so what do we have first? We get n k times n. Oh yeah. Okay, so this is okay, so let's say this is 2 to the log n, which is n, and plus 2 square root log n, which is the k, plus this one, which is 2 to the 4 square root log n. Okay. Okay, so this here is easy to estimate. I can say, yeah, if I take this one, it's at most log n plus 2 square root log n. That's a bit the same as saying k square is at most kn, so I can combine the two. Yes. Okay. So what do I have here? I have to simplify this further. So first let me connect C1 and C2. How can I do this without cheating? The C2 is given. It's the C2 was the constant that was hidden in these O's. And the C1, well, the C1 we can choose. It already appears here in the induction hypothesis. But it doesn't matter which value it is. There's one time I can choose it, because the theorem has a big O in it, and this C1 is the C1 of that big O, and I can choose what it is. I can choose how large I can choose it as I like, but the choice must be made independent of n and k. Otherwise it would be cheating. I cannot choose in every step of the induction proof a different C. That would be wrong. But I can, for example, assume that the C is bigger than the C2. That would be okay, because C2 doesn't depend on n. I will make such a choice, but not exactly this one. I assume that the C1 is greater than 4C2. Which I can do without loss of generality. Okay, so then I can write this one as 1/4 C1. Okay, let's take the C1 out here. And let's simplify a little bit these expressions. Okay, so what do we get here? So I get a log n, 2 to the log n. This comes from here. Then I get a 1, which comes from here in the exponent. This comes from here. And then I get Ah, yeah, okay. There's a k. So what's the k? The k is 2 to the 2 square root of log. Okay. Now here I have here okay, let's say this is plus. Okay, let's first do this one. This one is 2 square root log n, and then minus log k. But the log k is 2 square root log n, because the k is 2 to the 2 square root log n, so its log is this exponent, and this means that this here and this, they cancel each other, and I'm only left with this expression here. Okay. Okay, so this is plus 2 square root, and now I have to split this again, log n minus log k. But I just said that log k is 2 square root log n, and the whole thing under the root. And then I'm here. But I also have here twice this after this estimate. This term is the same as this term, so I get twice this term, but I have times 1 over 4, so this cancels with the twice and gives 1/2 times 2 to the log n plus 2 to the square root log n. So I hope it's still correct. If not, write something in the notes, in the comments. We are still not finished. I still have to do an estimate. Now let's look at this nested root. This is we cannot use this. We have to make that into something that looks like where we are going. And where are we going? We want to have, in the end, it should look like this in the exponent. Now this one is already there. It's here. When we have the 1 here, that is too much. This should go away. This one already did go away. And what we can afford extra is a 2 log m. So it would be cool if this one turns out to be bounded by -1 plus 2 square root log n. That would be good. And it is. So this is something you can prove by means of calculus. So this is where the assumption n at least 16 enters. If n is large enough, then this bound holds. Okay. Sorry, not exactly. So together with this one. So the 1 plus this 1 plus this is bounded by this. You can check this if you don't believe it. So let me write it again. So altogether this is C1 2 log n minus 1 plus 2 square root log n. Okay, and then we are through. Plus 1/2 from the other part, from here, 2 to the log n plus 2 square root log n. Okay. So now this is also 1/2 times 2 to the log n plus 2 squared of n, so it's the same as this one, and 2/2 is 1, so this is C1 2 to the log n plus 2 square root of log n, and that's what I wanted to show. Okay. I said at the beginning that the reason why I'm doing videos is because there is not, experience says that there's not much discussion in class. Well, maybe this proof is an exception. Here I'm typically making mistakes, and the students help me to fix them. Now you can't help me remotely, but if I got it wrong, if I got something wrong, please write it in the comments, and we can discuss it in the meeting. Okay, so what about this algorithm? The algorithm says, the conclusion is, the first thing that we saw is we can get O of n1 plus epsilon for every epsilon positive. This means we can get arbitrarily close to linear time. Arbitrarily close, but still with a fixed gap. We can make the gap as small as we desire, but we can't eliminate it completely. And the second one is an improvement over this, because it's better than each of these algorithms, no matter how small you choose epsilon, because the exponent itself also decreases to 0 as n grows. So this is what was it? So it was n to the 1 plus 2 over square root log n, and this is better than every arbitrarily small positive epsilon when n is large. And this is the point. Well, what does it mean, large? So this algorithm that I explained now and that we analyzed now is fast in theory. But it's not fast in practice, because the sufficiently large, somehow hidden in the O, what it means to be sufficiently large, is so large that you will never have any chance to compute with polynomials of such a high degree. So there's always the question of crossover point. So if you have algorithms, let's say they have a computation time t of n that depends on the degree of the polynomial, then you have the standard algorithm, where that is somehow quadratic, n squared, the standard algorithm. And then you have Karatsuba as an improvement over the standard algorithm, but Karatsuba obtains its efficiency by exchanging multiplications for additions. And that's a good trade, because an addition is cheaper than a multiplication, because an addition takes only linear time, and a multiplication, well, quadratic, or well, something that we don't know yet, but we want to make that smaller. But at least more than linear. So if you trade addition against multiplication, you win something, but only asymptotically. If you have very small polynomials, then Karatsuba is not a good choice, because you are trading 1 multiplications against 7 or 8 additions, and these additions also cost something. So Karatsuba takes over only at some point. And where is this point? That's something that you better don't try to determine in theory, but you try to determine experimentally by programming the algorithms and then just measuring the time or counting the number of operations that it needs. But in principle, it looks like this. And here you have Karatsuba's algorithm, and then here you have a crossover point. from here on, Karlsruhe beats the standard algorithm. And that's not so far outside. I don't know exactly where it is, but I imagine that for n around 100 or so, you will be beyond the crossover point. And then the other algorithms will at some point overtake Karlsruhe. Okay, so you have this T3 algorithm, which has again a crossover point, but it's later. And then there's the T4, which has a crossover point that is again later. And okay, this picture is not very accurate, because if you really draw, experimentally determine the crossover points and figure out where they are, you will see that the distances between them get larger and larger. Not like here, but they double roughly. They double when you go from TK to the next algorithm. But that means that if you want to reach really an algorithm that has n to the 1.1, for example, as runtime, you have to get to quite a large k, because you remember that this came from a logarithm, and the logarithm doesn't go to 0 very fast, the 1 over logarithm. Or logarithm goes to infinity, but not very fast. So 1 over logarithm goes to 0, but not very fast. So you have to take a very large k to achieve this exponent, but then you have an algorithm that corresponds to this that overtakes the other algorithms only at astronomically large degree. And that's not helpful. That's nice in theory, but it's not nice in practice. And from next time on, we will discuss algorithms that are not like this, and we will also never again see such a complicated complexity analysis. So it will get more simple. Well, yes. Maybe I should say that I don't know how to avoid it, that parts of this course are a bit technical. It's not always like this, and mostly it's not like this. But in order to get the things right, you have to worry about indices and whether this is +1 or -1. And I don't like to do this because I get this wrong all the time. I will try to teach this course as much as possible without the focus on technical details. But I also don't want to oversimplify things. So I want to tell you the things how they really are. But I don't want to get lost in computations that serve no purpose except of confirming that yes, it's true and it really works out. I want to show you the ideas of the algorithms and the intuition of where the speed up and the efficiency comes from. So I try my best to avoid technicalities as much as possible. Again, you can find all the details and all the full proofs in this book, and they really made a huge effort to not only get the things right. They got the things right most of the time, but they also made an effort in determining for many algorithms the constant that is hidden in the O, so that you can compare algorithms that have the same big O complexity but different constants. And here the analysis as it's carried out here in the book gives you for many algorithms also the multiplicative constants. So this is a very useful source, and it contains full proofs and all the details. I will not make an attempt to carry out the detailed calculations that gives you the constants. We will go a bit more slowly. Another question is, what about matrices? Matrix multiplication. Matrix multiplication, so it's another topic that will concern us very much in this course, but it's natural to discuss it a little bit at this point, because there is a relation to Karlsruhe. So what is the task? You have given two matrices, A, B, in K, well, let's say R, n times n. Find C, the product of these two matrices. The standard algorithm takes cubic time, cubic number of operations in the ground ring, and after Karlsruhe's idea came up in the 50s, and when Karlsruhe showed that you can multiply polynomials faster than quadratic, then people looked into whether the same idea can also be applied to matrices. So the idea is you write A and B like this. This is A and this is B, and you split them in the middle as we do with Karlsruhe, but you split them horizontally and vertically, so that you get 4 quarters for every matrix. And then you see if you can somehow get the 4 quarters of the result. So if you call this A11, A12, A21, A22, and so on, B11, B12, B21, B22, then the block in this corner will be obtained as A11, B11 plus A12, B21, and here similarly. And this gives rise to a recursive algorithm, because you can say, okay, in order to compute the product of A and B, I divide them in this form, and then I have to do 8 multiplications of matrices of half the size. So here, this is 2 multiplications for this quarter, but then there are 4 quarters, so there's 8 multiplications altogether. And 8 multiplications, that's bad, because that means we have a recursion that says t of n is bounded by 8 times t to the n half plus O of, and then the time for the addition, which is n squared. From here it follows that t of n is O of n cubed, so there is nothing achieved, but that's not surprising because we didn't do anything. We just said split in the middle, and this has no effect on the computation compared to the standard algorithm. You're doing exactly the same, you're just doing it in a different order. That doesn't help. Of course, this doesn't help anything. But then Strassen observed that you can do the same thing with 7 instead of 8 multiplications. I'm not going to give you the formulas, they're not so illuminating. But there's a way, similar as Karlsruhe found a way to do it with 3 instead of 4 multiplication. Strassen found a way to do it with 7 instead of 8 multiplications, and this brings down this exponent to log 7 to the base of 2, which is 2.8 something, 81, I believe, 82. Okay, whatever. So this is better than this is better than cubic, and it's better than cubic not only in theory but also in practice. I don't. Sometimes in textbooks they write this is only of theoretical interest, but that's okay if the textbook was written in the 60s. It's not okay if it's a modern textbook that just copies from a textbook that was written in the 60s, because nowadays this algorithm is really used in practice, because a matrix of size 100 times 100 or even 1,000 times 1,000 is not big. It's not out of reach anymore for modern computers. The question, however, is, can you do better? So we have seen for Karlsruhe that you can gain something by not splitting in the middle into halves, the rows and the columns, but splitting into smaller sizes. So what if we split A and B into thirds instead of quarters? Yeah, so the usual algorithm that would do this, so the usual algorithm for computing 3 by 3 matrices takes 27 multiplications. And here you have thirds plus O of n squared. And of course this doesn't give us anything, so it gives you the log 23 to the base of 3, well that's 3, like before. But you can ask yourself now, how much can you bring down the number of multiplications that you need to carry out in order to multiply two 3 by 3 matrices? Well, that's a challenging exercise. You can try. How far you get. The best that we know is 23. Okay, so that was found in the 70s and has never been improved since then. And rumors are that it cannot be improved any further, but there's no proof that the 22 is not possible. The problem is, this doesn't help you because it gives you here an exponent of log 23 to the base of 3, and it's not obvious how to compare this, but if you type it into a calculator, you will see that log 2 to the base of 7 is less than log 3 to the base log 23 to the base 3. So that means Strassen's algorithm, this one, is faster than this one, and it doesn't help you to split the matrix into 3 parts instead of 2 parts, at least for as much as we know. So nobody has ever been able to improve this 23, and even if you get from 23 down to 22, it's still bigger. You need to get down to 21, so you have to save 2 more multiplications if you want to beat Strassen. Okay, so that's a thing you can try. You can also do something different and say, okay, maybe 3 is not a good k. What about if we split it into k pieces for arbitrary k? That's also what saved our computation time for polynomials. So let's say we have k pieces in this direction and in this direction. And how many multiplications do you need to multiply 2 k by k matrices? There was somebody who figured out a way to multiply k by k matrices using 1/3 k cubed plus 6k squared minus 4/3k multiplications. So this can be done. This is multiplications in the coefficient domain. Okay, so what does this help? This means, so for fixed k, therefore, for every fixed k, this yields, if we apply it recursively, an algorithm. So of course I can multiply n by n matrices now also with this scheme, but I'm not going to save anything because there's a 3 here, so it's still a cubic algorithm. I'm going to get something out of the 1/3. Okay, so this leads an algorithm with cost t t of n equal to O of n to the log to the base of k of this expression here. So 1/3 k plus 3k squared times 4k. And unfortunately, if I let k increase, this exponent does not go to 2. 2 is what you would expect for optimal matrix multiplication algorithm. Like we had 1 for multiplication of polynomials, because polynomials have an amount of data n, n coefficients, or 2n coefficients. I expect to be able to multiply them as fast as they are big. That's what means linear time. Now for matrices, a matrix of size n is really a matrix of size n squared, because it has n rows and n columns. So I cannot hope to multiply matrices faster than n squared, because they are n squared big. The problem size in this case is n squared. Usually it's n, but for matrices it's n squared. What we want to find is an algorithm that multiplies matrices in quadratic time. That's the best we can hope for. But we don't have this, and this doesn't give it, because the limit for k to infinity of this expression, log k polynomial, is not 2. This is sad. The function here in the exponent is so that it starts somewhere, it goes down, and then it goes up again. Yeah, you see, it actually goes to infinity, because you have log k of k. Well, anyway, it doesn't go to 2. But you can ask, is this, yeah, what is the best k? So if this goes down and then up, then there must be somewhere a k for which is the best choice here. And the best choice is 70. This is where you get the smallest exponent from this approach. Smallest exponent from this approach. And what is this exponent? Well, it's this. It's 796. So it's just a little bit smaller than what we had with Strassen. And in Strassen's algorithm, you divide in halves. So if you think you have a matrix of size 256, you can divide a few times into halves. You can do it 8 times, because 256 is 2 to the 8. If you do this one with 256, you can divide once, because if you divide 256 by 70, the result is less than 70, so you can't do it again. In order for this to take effect, the matrices already have to be so big that you will never see in practice an advantage of this algorithm over Strassen's algorithm. And that's very disappointing, because it says that we don't understand matrix multiplication as well as we understand polynomial multiplication. We understand it a little bit better than this one in theory. So best exponent known. This approach here, this refinement of Strassen Strassen is from the 60s, and this here is from the 70s. But people have spent an enormous amount of effort in finding better and better matrix multiplication algorithms, where better and better means smaller and smaller exponents. And the best that I have here in my notes is something in this in this range. And from time to time there are papers published that improve this exponent, but they improve it somehow very by a very small amount. And all these algorithms are only of theoretical interest, because Strassen's algorithm is not. Strassen's algorithm is really useful, but these algorithms that have smaller exponents currently are not useful. So they are also semi-fast. Semi-fast as this multiplication algorithm that I showed you today, fast only in theory, not in practice. And for matrices, there's nothing better we can do. We have Strassen's algorithm. Okay, this is better than cubic, but better than Strassen's algorithm, everything that we have is only theory, which is very interesting, but not good for computations. For polynomials we can do better, and next time I will show you how to multiply polynomials. We will discuss polynomial multiplication now in two steps. First with a few assumptions that makes it easier, and then without these assumptions. That requires then a little bit more, some additional tricks to get around these assumptions. Okay, and these are algorithms then from next time on that are fast in theory, actually faster even than what I showed you today, also in theory, but not only in theory, also in practice. Okay, so this is a good breakpoint. Thanks for watching, and see you next time.